B.2, efficiency analysis of binary search. Actually, the implementation procedure is pretty straightforward. So let us just do the analysis, because when we do analysis, at the same time, we go through the implementation details. All right, so let's look at the, analysis part. All right, so for the question, binary search question, let us use a diagram to understand elimination. How much data can we eliminate at each step? All right, here I want to, do a chart to, show you step by step how do we reduce the problem size step by step. All right, number of comparisons for the worst case. In our analysis, our goal, so this is our goal. Goal. That's correct. All right. This is our goal. Number of comparisons for the worst case. All right. Let me use a diagram. So this line segment represents the whole array. All right. Then, when we do the first comparison, we drop one of the two subarrays because they have the same size. So it doesn't matter which one we drop. The next round, our second comparison, another one in the middle, we will drop another smaller subarray. We do this on and on, then we want to see what is the last comparison. So the first important question at this point, how do we determine the last comparison? How do we determine that? So here, if based on the data size that corresponds to each comparison, we have this. After first comparison, the data size becomes 1/2 of the original size. Original size and approximately 1/2. You may argue +1, -1. That small difference is not important. Just approximately n/2. Second comparison, n/4. After kth comparison, n/2 to the kth power. Okay, all right. Now we use this expression. We want to determine at what time should we stop splitting. We cannot do splitting forever. We have to stop somewhere. So the termination condition, we need to make our decision which comparison is the last one. After that, we don't need to do any comparison. That point is critical here. So here I want to do the analysis in this way. After the last comparison, the data size, if the data size is less than 1, strictly less than 1, then we should stop, right? The data size is less than 1. Why you want to split it, right? The data size is less than 1, you should not split it because it cannot cover 2 elements. The data size here, we use the length of the line segment. If the length of the line segment is less than 1, it can only cover at the most 1 element, right? only one element, you do not need to split it anymore. Yeah, so that's the critical condition for us to make our critical decision. Yeah. All right, so here, I use the math formula to find that K. Find that K. Yeah. All right. Data size less than 1. So this is the data size, right? Yeah, data size here, expression should be less than 1. Yeah, strictly less than 1. If it equals 1, theoretically, it can still cover 2 elements, right? Yeah. The length is exactly 1. It has some chance to cover 2 elements. If 2 elements, we can still make 1 split. Yeah. So that's why we make it strictly less than 1. Then no chance for another split. Yeah. All right. But we also need an upper bound. Yeah. Its previous problem size. Yeah. Its previous problem size. Yeah. N over 2 to the k minus 1. That size should be greater or equal to 1. That means we can make another split. It's previous. So here we have the 2 inequalities. Yeah. Then these 2 inequalities can help us determine the range for the k, the expression for that k. All right. So after simplification, yeah, so you know how to do it. Yeah. Then take a logarithm. Take a logarithm. Yeah. So we have this. We have this. Take a logarithm. Okay. Log base 2 of n between these 2 integers. K minus 1, this side less than equal. There is an equal part. This side, no equal. Yeah, that difference is important. Okay? We want a very precise formulation. So that little detail, we want to also pay attention to it. Yeah. Next. Now, the worst case. We want to write expression of k in terms of n. That's our goal. Okay? Yeah. All right, so let's do it. Derive the worst case formula. Okay. All right. We start with this expression. Yeah? So you can see from this formula, you can derive that easily, right? Yeah. So it's not hard. You move 1 to this side, you get this part. Yeah. All right, after that, then, so let's look at this. Yeah. Because we start with this inequality before. All right. The reason we go back, because this less than, strictly less than sign, we want to improve it a little bit. Improve it a little bit. How to? Yeah. N plus 1, yeah, n plus 1 less than or equal to 2 to the k. Because n is an integer. An integer strictly less than another integer. 2 to the k, another integer, right? N integer strictly less than another integer, then n plus 1 should be less than or equal to that integer, right? Yeah. So in that way, we improve a little bit. So you can see this inequality is slightly better than the original one. We improve plus 1 less than or equal to 2 to the k. That improvement, you know, has its own value. Yeah. All right. Then now we take a logarithm. We have log base 2 of n plus 1. This time not n plus 1 less than or equal to k, and then k less than or equal to 1 plus log base 2 of n. So we derived this important inequality. Okay? This important inequality. All right. Then conclusion. At this point, we get a conclusion. We have two formulas to represent that k. Two formulas. The first formula, k max. K max. Why I use the max? Because the maximum number of comparisons we need for the worst case. So the max. K max equals seeding function. Yeah. The seeding function. Seeding function is still less than or equal to k. Yeah. So that one. The first formula. Second formula, floor function of that side. Yeah. So these two, you can see expression is different, but their value are the same. Why the value of these two the same? Remember in our we used that formula before, remember? We used that formula before. I gave you the page number in our textbook, Appendix B. Yeah. Yeah. 478, something like that. Yeah. So we learned that formula before. Yeah. So that is the formula we learned before. Okay? Yeah. You go to Appendix B, you can still find it. Yeah. All right. Best case. Now, our final conclusion. The best case. One, the median. That's the best case. Yeah. Worst case. Here, we have the worst case. This one. Yeah. We just pick one of the two formulas. Yeah. Then average case. We know average case is always the hardest among these three cases. Can you find the average case? Let me ask you another question. Can we say average case is this formula? It's not. It's wrong. It's completely wrong. The reason is simple, because when we look at the average case, we need to factor in all the possible cases. All the possible cases. And those cases occur in different frequencies. In different frequencies. So that's why the average cannot be simply you just add 1, the best, the worst, divided by 2. No, you cannot. Okay? Yeah. Now the question. What is the average case efficiency? How to calculate that, right? How to calculate that? Yeah. Not very easy. Yeah. But here, I want to show you that. I want to use example where n equals 7 to show you how to do the calculation. Yeah. Here, let me quickly use a diagram quickly to show you how to calculate the average case. All right. Analysis for average case. I just give you the main idea. Yeah. You can easily generalize this idea to the general case. Yeah. Data, 7-element sorted array. Yeah. I use this diagram to represent these numbers. Yeah. Then, when I do the comparison, I want to draw a binary tree. Yeah. All right. So the assumption, let us make the assumption V is in the array. Otherwise, if V is not in the array, then, we have the situation when we do the linear search, right? Not in the array, so we need a probability P. Yeah. Here, in order to make our discussion as simple as possible, I make this assumption. okay, in the array. So otherwise, we need to use the probability P. Okay, yeah. All right. Draw the binary tree. The first comparison, we compare V with element number 4. So we put the element 4 at the root of the binary tree. Then we need to go to left branch or right branch, 2 possibilities. Okay, this element 4, we need 1 comparison. That's simple. Then 2 branches, left branch, right branch. Element 2 is the root of the left subtree, because the next one we need to compare V with 2. Element 6, right branch, the root of the right branch. These 2 nodes, if we compare V with these 2, we need 2 comparisons, and so on. Then 1 and 3, 5 and 7, next level, we need to do 3 comparisons. So 7 cases we organize in 3 levels: level 1, level 2, level 3. All right, now we are ready to calculate the average case efficiency. Here, let me write the formula. Okay, total case 7, so we put at the denominator. The numerator, we need to put in all the cases. Level 1, 1 node, 1 comparison, 1 times 1. Level 2, 2 nodes, 2 comparison, 2 times 2. Level 3, 3 comparison, 4 nodes, 3 times 4. Adding up, you get 17 over 7. Here, one thing I want to point out. When we talk about average case efficiency, we do not require the answer to be an integer. Fractional number is okay, because average usually should be non-integer fractional number most of the time. Only in a very special case you get integer. Some students, I noticed that some students, because they feel number of comparisons can only be integers, right? For worst case, for best case, it's true. But for average case, although each case, it's an integer number of comparisons, but when we take average, then it's not an integer. In general, it's not an integer. So it's okay. All right, so here I finished the B.2.